fun. It's no longer, I can say it's imaginary, but we didn't really use the calculators all that much for imaginary stuff, so we don't have to worry about that. But we will not be using calculators from here until forever. Well, I started trying pacing it out a little bit more, looking at what sections, like the order I wanted to try and do stuff this year. I always try to switch things up just a little bit to improve on what we've done before. And my best guess is that we will get through most of the trig stuff aside from the graphing portions of it, and that'll take us up to spring break. We get back from spring break, we'll take probably a week and a half to get through the graphing portions, and then we'll get into conic sections, and then we'll get into sequences and series, and then we get into probability statistics. Each one of those last few units, conics, sequences and series, and probabilities, they're all about week and a half, 2 week units. They're real quick ones. Usually it's just go through all the material, take a test. Go through material, take a test. I usually don't quiz in between all of them just because there's not as much to them. The trig unit, like I said, is the big majority of the second semester, so that's the way we set these things through.
Bro, that's not cool. I don't even know that.
Yeah, you do. Your phone's still on, that's why.
It's not. It's not. Why is your hand in the fucking
All right, here we go. General angles and radian measures. So what we've got here today is we're going to kind of start talking about how angle measures work within trigonometry. We're going to talk about what's called radians, and we're going to talk about coterminal angles and reference angles. Okay. As we go into this stuff, this trig stuff becomes unbelievably visual. It is imperative that you're writing things down as you go through these things, as you do these things. Because the more you write stuff down, the more it becomes easier, so you don't make dumb idiot mistakes. So, when we get to trig, we're going to start talking about angles in what are called standard position. When we talk about things that are called angles in standard position, that means they have to be placed in a specific spot and they have to rotate. Okay. Now, what I always like to do with angles, I follow the way the books and all that stuff do it. Let's kind of blow this in here just a little bit. Move these over. What we have here is we start with coordinate plane, just like we always have, x, y graph. Okay. Our initial side always starts on the x side in the first quadrant, and the angles, if they're positive, they move counterclockwise. Okay, so they open up to the left. Yes, backwards, so I can figure out which way I'm looking at. Right? Now, what happens is you have your initial side on the right. The vertex is always at the origin. Okay? The vertex will always be placed at the origin. The angles open up to what we call the terminal side of the angle, the other side. Okay? The terminal side lies within specific quadrants. It could lie in the first quadrant. Remember how the quadrants go? Quadrant 1, 2, 3, and 4. Okay. They could also land on what's called a quadrantal. That's a new term. I'll just bring that in here real quick. We don't work with them yet. We'll talk about more of those Wednesday. Quadrantal. I'm not making up that word. A quadrantal is if you're on the axis. The angles that are on the axis are 0, 90, 180, and 270. And any repetition of them. Those are the quadrantal angles. Okay? So your terminal side will land, if it's positive, it goes counterclockwise. If it's negative, it goes clockwise. In geometry, we always talk about not having negative angles. I think you guys remember that. We said that there was no such thing. There technically was. It was just a different direction. Okay? So what I want to look at is how do you draw and place. Yeah. How do you draw and place 110 degrees? You do. So if I want to look at a positive 110 degrees, I know that positive angles go open to the left. So what I would do is just draw an axis. And it's nothing too crazy. You're just trying to figure out approximately where it would lie. Everybody's okay that vertical is at 90, correct? And 110 is how many degrees off of 90? 20. So we know it's not going to be over halfway. So I would just draw it as here, and I'd write 110. Okay? As I'm starting to place these angles in the XY coordinate plane, what I want us to start to think about, and it's not really super important yet, but it is something we're going to use a crap ton for, all intents and purposes. It's a good word to use. We're going to use what's called a reference angle. A reference angle, a reference angle is how far the terminal side is off of the x-axis. Okay? How far the terminal side is off the x-axis. If this is 110 over to here, how many more degrees does it have to get to the 180? 70. So its reference angle is 70 degrees. The reference angle is how far is it off of the axis. Okay. Does that make sense? Yes, sir. Great question. Okay. Reference angles are going to allow us to do all of the trick stuff as we get into probably tomorrow, or sorry, more into Friday and then into next week. Okay. Reference angles are probably one of the most important things that we use. So I figured it's not all that terrible just to get used to how do you work with them. That's why I introduced them right off the bat. Okay. Another example, if I want to say negative 240 degrees, that means we have to start again, XY grid, and I'm now moving clockwise. Okay. So 240 degrees, does that go past 180? $240 is more than 180. Is it more than 270? No. So what happens is when we go to plot this one, we're moving the other direction. We still start with our initial side at 0. We move around, and it comes up here. There's our negative 240. Now that one landed in what quadrant? Second quadrant. How far is negative 240 off of the 180? How much further did I go up above the 180 as I passed it going negative 240? Okay. Now is that reference angle positive or negative? Positive. Very good. All right. It's still distance away from that, so it's got a 60-degree reference angle. Reference angles will always be positive. How far away? Because when you measure distances, you're always measuring positive distances. Does that make sense? Negative angles can have positive reference angles. No big deal. Right. Not terrible? All right. Oops. Try this one. Negative 130, and then give me a reference angle. Draw it, place it. What quadrant are you in, and what's your reference angle? I know, it's a lot of work. I ask so much of you. I'm assuming you guys got this. Negative came over here. You're in quadrant 3. Negative 130. How far were you off of the x-axis? 50 degrees. Because how much longer does it take you to get to 180? 50 degrees. Okay, that's how that works. Pretty easy, isn't it? What's that? Always. Reference angle is always off of off of the x-axis. That's why I'm starting it now, so that we keep practicing, so that when you accidentally do it off the y-axis, you'll learn before it's actually really, really important. Coterminal. Coterminal angles are angles that share the same terminal, or coterminal angles are angles that share the same terminal side. Basically, they have the same end spot. Okay. So if you think about it, if I look at, I'll come back to these two. If I look at 60 degrees, 60 degrees goes first quadrant. When you are in the first quadrant, what's your reference angle? It's whatever your angle is, because that's how far you were off the x-axis. See how that works? Yeah. First quadrant is its own reference angle. It's one of those little tricks. Now, when you're in this, how long does it take me to get back to 60 degrees if I continue to rotate around? 360 degrees. So if I start here and I go all the way around again, what am I at now? 400. So coterminal angles are two angles that share the same endpoint. Okay. What you do here to find coterminal angles is you're basically adding or subtracting multiples of 360. So a positive coterminal angle here would have been 420 degrees. A negative coterminal angle would be going the other direction to end up in the same spot. So I would take 60 and I would subtract 360. Where do you wind up at? Negative 300. So these two angles, the 420 and the negative 300, are all coterminal with 60. One of them's positive and one of them's negative. A lot of times what we look at are would give me one positive, one negative coterminal angles. Okay. Basically, all that boils down to being is you're going to wind up adding multiples of 360, or add up 360 or subtract the 360. There will be one rule, and I'll show you that here in a second, to how this is going to work. Okay. I'll do this one. So, to find coterminal. If your original theta is between 0 and 360, to get coterminals, all you do is add and subtract 360 to it. Okay. For example, we just did one with 60 degrees. If I say our original theta is 200, is 200 degrees within one revolution? You'll hear me say that a lot. When I say one revolution, that means one time around. Okay? Is 200 degrees within one revolution? Yeah, what quadrant does it lie in? Third quadrant. 200 degrees would lie in the third quadrant. What's the reference angle? 20, good. So it's 20 degrees off. Okay? Now, since that lies within one revolution, to get a positive and to get a negative coterminal angle, a positive coterminal angle would be 200 plus 360. So if I do that, I still start at the original, go all the way around, and I wind up with that 560. Okay? To get the negative, I do 360, subtract the 200, or I'm sorry, 200 minus the 360, where you're just coming down this way. And what you wind up with there? Negative 160, good. So you get negative 160. Yeah, the other one was 560. That's if your original angle is within one revolution. Okay. If it's not, you have to get it within one revolution to make it work. Okay. For example, so write this one. The other one is if theta is not within one revolution, spell add or subtract to get to. it sounds really weird for something that looks really easy. For example, if I use the one I had up there a second ago, 510 degrees. If I say 510 degrees, is that above or below 360? It's above, okay? So what that would look like if I placed it, I'd have to go around 360. There's one 360. How many more degrees would I have to go to make it equal to 510? Well, basically what you're doing is you're subtracting the 360 to figure out what's left. If I do that, I'm left with 150. We okay with that? Well, that 150 be placed in what quadrant then? Second quadrant. So I continue to the second quadrant. What's the reference angle then? 30, okay, so I'm 30 degrees off. Okay, so I'm 30 degrees off. This was at 510 total degrees. Since that was within one revolution, beyond one revolution, I have to bring it into one revolution to get its positive. I'm subtracting to find positive coterminal, because I have to get within one revolution, and then I subtract it one more time to get the negative coterminal. And if you do that, since you know what your reference angle is once you plotted this, to get your negative, aren't you going this direction? How many degrees is that?
180.
Negative 180, and I go up another 30. How many degrees is that then? There you go. There's your positive, there's your negative. See what I'm saying about how visual this becomes? It's so visual. And by finding that quick little reference angle, you guys are just wind up seeing, okay, I gotta get to 180, then I gotta move up a little bit further, or I gotta get past it a little bit further. And that's the easiest way to make this stuff work. Okay? That's how that would work if your original angle is beyond one revolution. Okay?
If you go back to the other slides,
No. Yeah, basically what happens is, if you're beyond one revolution, you have to either add or subtract to get it within one revolution to get your first positive or negative. This would work the same way if your original angle was, if your original theta, let's say, is negative 400, okay? Negative 400 is beyond one revolution. You okay with that? If I plotted it and I go negative 400 degrees, I'd have to go all the way around, and I drop down 40 degrees, okay? So in order for me to get within one revolution, I'd have to get to its first negative one. I'd have to add 360 to it. And if I add 360 to that, lo and behold, I'm at negative 40 degrees for my first negative coterminal. I would add another 360 degrees to it to get this side of it, which would have been 320 degrees. You're just adding, subtracting multiples of 360. Usually that's the weird one. People always tend to fight with that one when it's beyond one revolution. Just remember to just keep subtracting until you get within one revolution, it'll be okay. That's fine. And those are okay. The fun stuff. Radians. No, this is important. Well, I do put the FU in functions. How about the fun in functions?
Yeah, no.
Anyway, radians. As you guys all are aware, on the calculators, you have the button that says radians. And I always say, stay away from radians because you're never going to use a calculator to work with radians. Radians are another unit of measure as opposed to degrees. Okay? In our world, normal world, when we have our degrees, we start at 0, we go all the way around, and we get to 360. Are we okay with that? Now, we also would stop at halfway of 0 to 360 is 180. Halfway of that was 90. And then halfway between 180 and 360 was 270. So you hear me talk a lot about revolution, okay? Now, when you start thinking about revolution, what goes around and around? A wheel. Wheels are shaped as a circle. Okay. So, if I start with the idea of, let me make this a little larger. If I start with the idea of a circle here, if I start with the idea of a circle, it takes 0 to 360 degrees to get all the way around a circle. What's another name for the distance around a circle? Circumference. Okay. Circumference is what? How do you find circumference? That would be the area. 2 pi r. 2 pi r, which means your radius has to be defined, correct? So if I say my radius is 1, what's the circumference of the circle? 2 pi. Because 2 pi times 1 would be 2 pi, yes. Very good. So again, in terms of a radian measure is nothing more than parts of the circumference. Going around a circle is 0 to 360. Oh, sorry, I went the other way. From 0, yeah, I did the right way. I'm looking at you guys. 0 to 360. It's also 0 to 2 pi to get all the way around. Then when you guys did arc length last year, you converted arc length. It was the distance on the circle. You guys were actually working with radians. You just didn't know it. So you started at 0. To get all the way around a circle, you wind up at 2 pi. What's halfway between 0 and 2 pi? Pi. What's halfway between pi and 0?
1 half.
How about pi over 2? Now, if I sit there and I think of this, if I'm counting, remember when I called quadrantals a minute ago? 0, 90, 180, 270, 360? From 0 to 90 is how much pi? Half a pi. So if I go up a half a pi, then I go to 180, I went another half pi, right? So I go 1 half pi plus 1 half pi is 1 full pi. What's down here? 3 halves pi over 2. 3 pi over 2. Because then if I'm going up by halvesies, 1 half, 2 halves, 3 halves, 4 halves. Are we okay with that? Okay. What's halfway between 0 and 90? 45. So if this is 45, and then halfway between 180 and 90 is also another 45 in it. Wouldn't that be 135? And then halfway between here and here, I believe is 215. No, is it 215? No, 225, sorry, 225. This one's 315. So what's halfway between 0 and pi over 2? What's half of a half? 1/4. So at 45, it would be pi over 4. Now watch what happens. This is really easy to build. If I go up by increments of 45 degrees, I'm going up by increments of pi over 4, 1/4. So 45 is 1/4, 2/4, 3/4, 4/4. See what I'm doing here? I'm adding fractional amounts with the common denominator. 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, and 8/4. It breaks it into smaller chunks. Okay? So far, so good? All right. So let's see here. We've done 45s, we've done 90s. What are the other two angles you guys used a boatload of? 30s and? Gee, do you think those might be a little bit important here?
Especially on my triangle. I don't think so.
Oops. It's all made up?
Yeah.
Now, are you guys okay by saying, if I go up by 30 degrees, I go 30, 60, 90, 120, 150, 180, and so on and so on and so on? Okay. So what we need to do is figure out 30 is how much of 90? A third of it, right? What's a third of a half? Is a what? A sixth. So as you're going up through here, a third of a half to get me from 30 degrees here. So we have 30, 60, 120, 150, 210, 240, 270, 300, 330. What we do now, to go up every 30 degrees, we go up by a sixth. Okay. So pi over 6. Pi over 6, if I add a 6 to that, I get 2 pi over 6, but I don't like unsimplified fractions. What does that become? Pi over 3. Add a third to that, we have, all right, so 1 6, 2 6, 3 6, 4 6, which is 2/3. So 1, 2, 3, 4, 5 6. 6 6 is the whole. 7 6. 8 6, which is 4 pi over 3. 9 6 gives me the 3 over 2. 10 6 is 5 over 3. And then the last one would be how many sixths? 11 sixths. 11 sixths. Because if I add 30 degrees to 330, I'm at 360, which would make this 12 pi over 6, which is 2 pi. Now, I know this looks really, really weird, but I want you to remember, anything that's in the first quadrant gets replicated throughout the entire thing. What this is, what we just quickly made without too much of a hassle here, is called the unit circle. Okay? This is going to become your best friend, but you don't need to memorize it. Yes, you do. And you don't have to pay for them.
Yes.
So what's going to happen here is I just want to show you guys real briefly what radians are. Radians are part of the circle. Okay? What we're going to do today is we're not going to worry so much as far as how all of this goes into play with solving and working with stuff. This was just a really easy way of showing how we converted things. We converted from degrees to radians. Okay? When you guys did that last year, you had a formula for it. Remember you did central angle over 360 times 2 pi r?
Yeah.
When you did arc length?
Yeah.
Just not smiling.
Yeah.
Okay. So last year when you guys did this, you guys central angle over 360 times 2 pi r. That's how you guys did arc length. Okay. Now, in this case, our radius is always going to be 1, so I don't have to worry about it. Can I simplify that fraction? Bless you. What do I do with the 2 and the 360? Simplify, what do you get? 180. So basically what happens is to go from degrees to radians, we're going to take our angle, our central angle, over 180 times pi. And that's what you guys did last year with arc length, but your radius was arbitrary. Okay. So if we look back at what I did a second ago, if I said 30 degrees, 30 degrees was 30 over 180 times pi. Well, 0 dropped, right? 3 goes into 18, how many times? 6, pi over 6. That's how we convert. To go from degrees to radians, we multiply by, basically take the angle and multiply it by pi over 180. To go from radians to degrees, what do you think you have to do? The opposite. Yep. Radians have pi, degrees don't. Okay. So you want to gain pi when you're going from degrees to radians. When you go from radians to degrees, you multiply by 180 over pi, because you want to get rid of the pi, because the pi's will drop pi. So for example, if I have 7 pi over 2, and I wanted to convert that to how many degrees? Pi has dropped, right?
Yep.
And what's half of 180? 90. What's 7 times 9? 63, so this would be 630 degrees. Okay. That's what we're looking at about how we convert. We just convert back and forth.
So radians.
Radians 2 degrees is 180 over pi because the pi is going to drop. The degrees doesn't have pi. That's how. Because think of it, the radian value has a pi in the numerator. You want to be able to get rid of it, so you have to multiply by basically reciprocal, and that way it drops. Okay. Now, radians also can have reference angles. Radians are still, however far off they are within the axis. We can still place and draw radian value. This is when we start counting. Okay. Remember how I talked about before how much I despise mixed numbers?
Yeah.
This is where I like mixed numbers. Because sometimes you have to count. Okay. We count by pi's and stuff like that. All right. So we did this. So let's look at this. Let's look at how do we do 11 pi over 4. How do we draw that? And then how do we get coterminal angles out of it? All right. 11 pi over 4. Because we've drawn, what do you call them? Degrees. Now we have to be able to draw radians. 1 revolution in radians is how much pi?
2 pi.
2 pi. Okay. Now, in terms of fourths, because that's my denominator, 2 pi would be how much? 8 fourths, right? Are we okay with that? So, is this more or less than 1 revolution? It's more. So, this isn't a bad place to do a mixed number. 4 goes into 11 how many times? Twice, and how many are left over? 3. So this is 2 and 3 pi over 4, basically. If you think about it. All right? So if you start to think about, we go around 1 little, 2 little, 3/4 pi. What quadrant is that going to get me into? Very good. 3/4 pi. How much are you up off of the axis in terms of pi? In terms of pi? Pi over 4. Okay. Your reference angle will be pi over 4. Okay. Now, this was beyond 1 revolution, which means I have to bring it back within 1 revolution. So I subtract 2 pi, which gets me to what? 3 pi over 4. See how nice it is when you use a mixed number? This is where mixed numbers are good. All right. Now, the other one, if I have to go negative. If I'm going negative, I'm going the other direction. I'm going negative pi, and then I went up how much? According to my reference angle, I went up 1/4 pi over 4. So what's, that would be, if I'm thinking it, always keep it in terms of your common denominator. Common denominators would be pretty easy to work with. 1 pi is 4 pi over 4, correct? Negative 4 pi over 4, excuse me. And I'm going up another, so I'm up negative 5 pi over 4. And that's how you count them in infinite pi. Okay. I love ratings and stuff. Stuff is fun. Okay. Try not like.
Everybody's just running the.
Let's try negative 7 pi over 6. Let's draw it. Let's do a positive and negative coterminal angle of negative 7 pi over 6. So negative 7 pi over 6, is that beyond or within one revolution? It's within, okay? It's within. This is the same thing as saying negative 1 and pi over 6, or 1 pi over 6 if you want. You okay with that? So if I'm starting, I know I have to go clockwise. I would go clockwise a pi, and how much more do I go up? 1/6 pi, so I just come up the pi over 6. So my reference angle is pi over 6 off of pi, okay? Now, to get a positive coterminal, the positive starts and goes this direction. Well, how far is it off of the pi? It's 1/6 off, right? So
it would be 5 pi over 6.
very good. And that's why we keep thinking about it in terms of fractions. A whole pi with a denominator of 6 would be 6 pi over 6. Just move it up 1/6 and you're at 5 pi over 6. Okay? So there's your 5 pi over 6. If I go another negative, we already knew that our original angle was at negative 7 pi over 6. I just have to go around another negative 2 pi. But I'm not going to write negative 2 pi, I'm going to write it as negative 12 pi over 6. So what's negative 12 and negative 7? Negative 19. So my other negative angle would have been all the way around at negative 19 pi over 6. And all I'm doing is, I'm adding, subtracting 2 pi. But I'm only adding it in terms of 2 pi with that denominator. It makes everything easier. Radians are so easy to work with. Okay? They're so easy to work with. Okay? Okay?
Leave this alone, this is already.
You're ready for calculus. Let's see. Skip for calculus. Yeah. Honestly, the trick that you guys are going to go through from here, from what we started with the log cosines, log sines, and like you guys know how to draw pictures and whatnot. The trick that we do here is going to allow you guys to, whether you're in honors pre-calc or regular pre-calc, you're just going to kick ass. Really, it's such a foundational thing that the fact that I spend so much more time getting into why everything works. So when you guys get to the more complicated stuff, it's going to be a breeze. Okay, when you get to pre-calc, whether it's honors or regular, the only things that they're going to add to the stuff that we do is maybe 5 or 6 sections. Okay, and the rest is kind of all blended together. So you'll have a good foundational part for all of it, which I really hope that you guys will do well. We don't have time. I know we wanted to kind of do arc length in the area. We can kind of snap that out real quick tomorrow, so I'm not going to worry about that. So let's see. In the textbook, I have you guys drawing some angles, finding coterminals, and converting. That's all we're doing today. Okay. So, yeah, we're not going to do that one. All right. So I have the PDF up. I want to say it's on. I'll have the page. This is section 13.2. We're going to do numbers 28 through 58 evens. Okay. The first, when you're doing the drawing of the angles, the first one says 144 degrees. When you draw that, you guys okay? It's all in line with the second quadrant. Draw it, place it to the second quadrant, but do me a favor. I want you, whenever you draw an angle, whether you're finding coterminal angles, whether you're just drawing an angle, always list the reference angle. Get in the habit of listing out your reference angle now, so that way when it becomes super important to find them over and over again, you'll be good at it. Okay? How far is 144 degrees from 180? 36 degrees. So your reference angle will be 36 degrees. Okay? That's when you're drawing these things, that's what I'd like you guys to do. Does that make sense? I know it doesn't say to do that, and we don't really technically introduce reference angles until I think, yeah, they technically come in the next session, which will start on Friday. But it's really important to start learning how they get placed and how they look. Okay?
Yes.
Yay! But yeah, leave pause.
How did you
What is pause? In the